Next, we're going to have a presentation of a video from Argentina. And immediately after, we're going to have Roberto Candal from CONICET and San Martin University in his lecture, Nano, Organo, and Bio-Clays for environmental remediation. Well, good morning, you all. As soon as I have my presentation loaded, I'm going to start. I come from the National University of San Martin in Argentina, where I teach, and I'm CONICET researcher in the Environmental Chemistry Department, Energy and Materials. What I want to tell you, according to what I spoke to Edgar in the organization committee here, it is something we're doing in my research group, and also because of the topic, I want it with other colleagues, friends of mine. They are the ones, they are not the only ones, but the ones I know. This is to include a wider perspective of the presence of metalloids and heavy metals in waters. This is a guideline of my agenda. I'm gonna speak fastly on some topics or items. For example, economic analysis. As you can see, I'd like to tell you about status of pollution in some cases in Argentina, then after certain explanations on materials we're developing in my university and my laboratory, our laboratory in the university. Finally, sediment bioremediation. About metal pollution and metalloids, two typical examples in Argentina. They are not the only problems, of course, but they are two cases that are paradigmatic. One is arsenic in water, which is a natural process. And the other is heavy metals in sediments and water, where we humans are responsible for that, at least in Argentina. As Edgar said before, this is a map of the distribution of arsenic in Argentina. This is an incomplete map because day by day it is completed more, where red dots indicate polluted waters. There's a dense dotted area where most of the analyses were carried out. That's why there's more detailed information about those. And this is an area which is highly populated, devoted to agriculture. There are other areas that have a few dots, but in the north of Argentina, arsenic concentration could be higher than what we have here in Patagonia, where there could be less arsenic. It is because there's less exploration, as Edgar said. There's the need of monitoring air and water. This is Buenos Aires province, the most populated Argentinian area. This area of Argentina, this desert. Buenos Aires is the most populated area in Argentina. Colors indicate concentration of arsenics determined in these areas of Argentina, and as you see, this is a serious problem. This is a discovery that is relatively recent. Before, they didn't know there was arsenic in that area, and it is a serious problem nowadays. City of Buenos Aires is located here, and there's a problem of arsenic in the surroundings of Buenos Aires, and it is becoming a problem. This is serious because the population density there is very high. Arsenic, as I told you, arsenite, and mobility and state of oxidation depends on the conditions of water sources. Arsenic in waters, it is in underground waters. It is a natural happening. It is natural, and waters are underground. Another problem is heavy metals in sediments and water. I'm going to emphasize sediments. This is a river extremely polluted, existing in Argentina, close to Buenos Aires, Reconquista River. It is highly populated, and this is characterized for being extremely poor. Many people live under the limits of poverty in marginal areas with very precarious housing, where there are no sewers, garbage collection, and everything goes to the river, to the waters, particularly rivers and ditches that go around. This is a satellite picture of a neighborhood of the type I told you. It is a very humble neighborhood, and part of the waters go to a ditch or to a natural creek that goes to the Reconquista River, which is here. This is Reconquista River. This is a dam that is at an acceptable low level of pollution. This is a reference because it is close to an agricultural area. It goes through an industrial and highly populated area, and it goes to the La Plata River. This is the area, and these pictures belong. What you see, this is the information we have in our laboratory. This belongs to sediments, 3 metals: copper, chrome, and zinc, expressed in milligrams per kilogram. Numbers correspond to sampling places throughout the ditch, and this discharges sewer waters and other waters from companies that in a dark manner they discharge their waters into the ditch. Look at the concentrations in this point of chrome: 118 kilograms per kilo, and zinc 1.5 milligrams per kilo of sediments. This is more than a zinc mine. The sediments in this river is a mine of metals. This is combined by organic sediments. As I told you, sewer waters go there, so it is little healthy. And there's interesting thing. We studied the self-depuration of the system, the self-purification with a high organic load and heavy metals. These waters, soils that are clay containing, these waters have those clays, and this makes a rapid sedimentation and throughout the river and the ditch until going to Reconquista River. The concentration of organics and metals drops very drastically. They don't have very highly organic load. It is anoxic because with such an organic amount of load, metals stay in the sediment. These sediments are highly dangerous, hazardous. Many times these ditches are cleaned, and these sediments go to the surroundings. When they are in the shores of the river, these sediments have a lot of metals, and with bacteria and water, sun, etc., this oxidizes and this becomes sulfides and go to the solubilized water again. This is Reconquista River. This is the collection. Look at the chrome amount here. It is impressive, and it is because of the tannery industry in the country. This is located more than 100 years ago by dropping chrome into the waters. Nowadays they don't do it so much, but this is the history of 100 years of tannery industries there. And these are the guidelines proposed by the National Institute of Waters, that it is very under of what we determine in those sediments in that area. One thing to tell you, these are very reducing conditions. Sulfides and oxidized products appear. Now, some of the techniques of remediation, something I wanted to tell you. This is a set of things. I don't want you to understand everything, but this is just an idea. On other details, we could talk about them maybe tomorrow or in other time. What is Organo and Bio-Clays? Clays are aluminosilicates, and they are present everywhere. And they are kind of rocks, and they have silicates. In our particular case, mormorinonite It belongs to bentonite family. It is a laminar clay, aluminosilicate composed. It makes kind of layers, and because of electrostatic interaction, because of cations, sodium, calcium, that are lodged in these interlaminar spaces, these have intrinsically negative load, where aluminum has 3 valences replace silicium, so there's a deficiency of positive load that generates a negative permanent load in the interlaminar area. For this not to explode, there's the presence of cations that stabilize the structure. These layers, you can make very fine layers. Something interesting, you can set here an alkylic bond here, siltrimethylammonium. This replaces sodium, and it increases the interlaminar space. It changes the properties of the clay, and apart, these alkylic chains make it more hydrophobic, and it is able to absorb organic substances. So this is a way to modulate the properties of this material. There are some characterizations here. If you see it through X-rays, when you increase OATMA, it corresponds to the fraction of interplane space, and it displaces to lower angles that corresponds to a bigger interlaminar space, 124 nanometers to 2.04 nanometers. We're working in nanometric scales. That's why these materials are considered modified in nanoscales. The potential, what happens with the surface load in pH, this clay is intrinsically negative, but when you add O18Na, it passes through positive and it changes characteristics, and you can use it to focus in organic matters in water. We tried with a fungicide, the post-harvest that they use to protect citrics in the cultural activities in Argentina, and this is an isothermal of absorption. In function of concentration, it increases the imosalil retained in the clay, the modified one and the natural one. What's interesting is as follows. Look, we did an experiment of absorption at pH 7, neutrality. The clay absorbs 95% of imosalil in this solution per liter. An organic carbon, which is part of imosalil and excipients together with the base, are absorbed in 47%. Organo clay do it in a lower degree, which is positive, and we're working in a pH 7 of imosalil. Absorption doesn't have electrostatic strong absorption. What happens in pH 3? In pH 3, this substance reacts positively because we are under the pH neutrality. So you could expect that in the case of nanomonite, nothing could happen because it is negative. Desorption is 0, but in organoclay, it becomes 98% of absorption compared to the absorption at pH 7. If this gives us the strategy to absorb or desorb at one pH or the other, we can absorb contaminants. We withdraw sodium because of decantation, and now we have a dangerous pollutant because it contains a plaguicide. What you can do is concentrate it in a lower volume, cause desorption, and then after apply a technique, advanced oxidation. This is a process, I'm not going to give you details, in which by working with oxygenated and iron, oxygenated water, you generate radicals, very powerful radicals that are able to manage everything close. So we concentrate water, we withdraw sodium, we disperse in a volume 120 times lower and oxidized. What we observe is this. how the concentration change of imasalil once desorbed in function of time, and in a little time you can destroy it completely. Animasalil, not subproducts of oxidation that appear in this curve, where the organic matters start dropping after 2-3 hours of a treatment. Well, if not possible to eliminate all of the residues, the basic dangerous component disappeared, and you can treat it through biological activities. This is done through other type of works that we have done in our laboratory. This is the strategy to eliminate solution pollutants. Bio-Clays, that's what my colleagues call them in laboratory. This is what we do in our working group. Here we combine the capacities of absorbing the biomass, in this case fungi, with the capacity of absorption of the clay by metals. We're working with the mormorillonite. This is intrinsically negative. Metal cations many times are positive, so they could be absorbed and strongly retained because of electrostatic effect. What we observe in the laboratory, if you combine biomass, it has a lot of absorption metal capacity. It has a synergy with the clay, and it increases the capacities of absorption. This is the capacities of the Bio-Clay. These are images of one of the fungi we studied, acre. It is kind of a fiber combined with the nano clay. It becomes kind of leaves of a plant. And it has a very good effect. And if we analyze, this is isothermal of absorption for uranium. We also studied copper, and it has a very good absorption capacity. It is soluble in water, and these are isothermals of absorption, and the combination of the fungi, which are the black dots, it is more effective than working separately with the pure clay and pure fungi. And this is another variety alpha and other type of fungi. What we observe here in this information is that uranyl is introduced in the interlayer of the clay. Not only the biomass, but also in the interlayer. That's why the fungi, part of the synergy, is a consequence that now the two interactions are allowed in the biomass interaction and extension in the interlayers of the clay. Another use of clays, this is modified with iron oxide. In this particular case, we took the same clay. These look like flakes, and they are all intermingled, and we can modify them by depositing iron oxide particles. You can see them, and with this we have the possibility of transforming this into a catalytic element. Again, iron oxide is interlayer in the mormorillonite in different angles, and this is what happens with electrophoresis. It changes the surface load. It becomes more positive because of the presence of iron. This is what we use to absorb a color, which is violet. It is used in many parts. In medicine, violet, it is a cationic color. These are nitrogen, and this is quaternary ammonium. It is positively loaded electronically. Mormorillonite is intrinsically negative. Here you see the isothermals of absorption. In presence of iron, it absorbs the crystals of a color, violet color. It downloads reduces the load and absorbs a lot, 200 milligrams per kilo, and that's a lot, a huge amount. You can make a model, and it is interesting because if you wanna play, this is physicochemistry per SACS low angle X-rays. You can see how is the measure of this interface, and we observe in the violet presence there are two behaviors. In low concentrations, it increases the interlayers 0.29 to 0.49 nanometers, but with higher concentrations passes to 0.98 nanometers of, this is a dimmer. Now in the interlayer there's the absorption of this interdimmer. This is explained with a model. Simply how to play with these clays, and apart from what you can learn from applied activity, you can learn better how the nature works. Once absorbed, what do we do after? Then after, you have a waste, a residue that has low volume, because not look in a textile industry, cubic meters per hour in a lower color concentration. You notice you have to collect all, concentrate it, and then after, what do? What you do currently, you take that clay, absorbent clay, to a sanitary filling, but you have to pay. An alternative is, once absorbed the color, you oxidize with a physicochemical process, and then after, in this chart, you see with several treatments, several iron concentrations and other applications of iron, there's a noticeable decrease in 1 hour of all of the violet crystals that are already absorbed in that clay. What is also observed is that as the concentration of violet drops, organic matters are released because of the oxidation. So they detach from the clay and they enter into the solution. Luckily, it lasts very few time, and it goes to a very good value, 5 milligrams per liter, which is acceptable. This is when we only used the unmodified clay. The violet crystals drop, but not much. This was not a good experiment. If you see the organic substances compared to the solution, they don't degrade after the treatment. The combination with iron is very good, a feasible solution. Another material, which is zero-valent iron in monoparticles. This is a work by a colleague, Marta Litt, a specialist in the use of nanoparticles and nanomaterials in remediation of environment. She worked with a company that is located working with nanofen and nano iron particles that work for abating arsenics in water. This is a model by another author that tells us that a particle of iron is covered by a film of iron oxide. This is very attached to the arsenic. I think this becomes an ally with arsenic and iron, and this is a system that relatively you can take it away from water and you can have clean water again. These are other charts where the use of ultraviolet light has a benefit action by oxide reduction phantom reaction by causing absorption into the clay. You need to test several variables of work. For example, lighting with ultraviolet light, UV light, and other substances treatment in water. This could play a very important role in improving removal of arsenics. This is another example of arsenic removal. This is P-varied clays. They have iron. The difference is that they are calcinated. This is pillared clays. This is used for remediation of arsenic in water. And look, it shows the percentage of arsenic removed. 50 ppm, even 160 ppm. Limit concentration of arsenic in water tolerable is 10 ppm. So this is good to have good condition water, potable water, drinkable water. You need to continue working with these trials. You can make some filters, or at the scale, as Mr. Edgar said before, remediation of sediments. This is continued with the conference, as we saw before, is the use of bacteria to remediate highly polluted sediments. The idea is to use a type of bacteria named as sulfur oxidizing, and they are able to take sulfur electrons and make them into sulfuric acid. What it generates is acidification of the environment, which without control takes to the acidification and pollution of the environment because of dissolution of metals. But if you do it controlled manner, you can eliminate those metals from the sediments and you can incorporate them, and if you can pay the cost. This is what we did, and here we see these charts. This is the work on publication. This is the concentration of zinc, and this is other pH. This is the time in days. In this particular experiment, they worked in a batch. So we set sediments in water, inoculated with bacteria, with Acetobacillus. The system inoculated was left in agitation, and periodically zinc concentration and pH was analyzed. pH dropped when adding sulfur, which is giving electron for these microorganisms. In presence of sulfur, the pH drops. This is sulfuric acid, very strong acid, and as the pH drops, it releases zinc. It wasn't possible to recover it after. This is a decontamination process of the sediment. What you can do is in piles, biohits or something like that, where you can see how by adding several contents of sulfur incorporated to the sediment, which is inoculated with Acetobacillus, this obtains a release of zinc and copper in the case of the bars in the chart. This curve here, these bars that you can see here, improved the extraction of zinc and copper present in the sediment. This corresponds to a case where they dusted sulfur on the sediment. So this allowed the oxidant enter into contact with the sulfur, release electrons, and it recovered up to 60-70% of zinc present in that sediment originally. These are the sediments I showed you in the charts. Remember that they had 1 gram per kilo, 1 gram of zinc per kilo of sediment? And for instance, this is what you imagine of a remediation system for sediments. This is just an example of biomining, where you use the same bacteria to leach minerals present in sediments, especially taken from the earth, and especially to recover those metals. This is to purify sediments. This is kind of a pilot program. This is a case that I cannot explain much because I don't have much time. There are people who is devoted to study analysis of cost-benefit to see if, for example, the purification of waters, of arsenic polluted waters, the improvement of this quality of water is benefit or not, and see what procedures studied are more economic. They work in Cordoba province in the center of Argentina. If you remember, that was one of the most arsenic content waters. This region, it is a province named La Unión. So we wanted to see if there was an improvement in arsenic content and quality in water according to the process used. They used 4 methods. One is Auflock, which is kind of a sachet or a bag with an oxidizer, which is chlorine, not gas but hypochlorite, clay activated with a high absorbent capacity, chloroferric aluminum sulfate, and nothing else. This is added into water. It makes a flocule, kind of a gum, which decants and drags arsenic. And the other is zerovalent use, iron use. This was Virulano. It is iron wool that you use to clean the pots in the kitchen, and an iron-rich soil taken from the province of Bendiciones. There's an hydrogen treatment which is using aquatic plants that are able to sequestrate, to kidnap arsenic, to take it out from water. What we observed, this is the net present value, add up benefits plus costs, etc. of this technology, and a study was done where there are many premises: speed, rate of discount, correction parameters. It is a complex analysis, and you can do it. Of course, it exists, and the great difficulty is that it is difficult to grant value to a public good such as water, because water sources don't have a market value. They don't. They are not offered in the stock exchange. So, what is the value of this water? We don't know. This is just benefit, because the benefit is seen in health. The population doesn't have to go to the doctor so often, and this has a cost. It is an economic benefit for the states or for anybody paying for that health service. Well, you can take that into consideration, and as a result, the zero-valent iron is the champion. It is the best working solution. Some conclusions. Well, there are pollutions, anthropogenic or natural, that exist in LATAM countries that have a strong risk for populations, especially those who are in poor areas. So these people need immediate solutions. We cannot go around and leave people get sick and die. We have the technology, we have methods in order to do it and purify water. Of course, they are necessary to implement. Of course, we can do it from the science perspective, but those decision makers could make our mission. We could give them all the tools for them to do it. Well, these Bio-Clays are catalyzers and combination with biomasses. This is a technology that also works. Zero-valent iron is also good to eliminate arsenics and other metals. Zero-valent iron is good also to remove chrome. And finally, they are kicking me out from here. So I thank all these people. Thank you, Colombia and Colciencias. All of the institutions working here in Colombia and those who are present here and those who to work in this project. Thank you.